Okay, in this video I'm going to talk about the iodination of propanone. This is an apparently straightforward reaction with two molecules of reagent, one molecule of propanone, one molecule of iodine, reacting to form the products. As such, since there are only two molecules involved in the reaction, one would expect a rate expression as follows. Where the rate equals the rate constant times the concentration of propanone to the power of 1 times the concentration of iodine to the power of 1, where both reagents are first order. It is, however, found that this is not the case. This reaction does in fact require the presence of an acid catalyst, which is represented by the H+ sign, in order to proceed at any reasonable rate. And the true mechanism, the true expression is actually found to be via experimentation. First order with respect to the propanone as expected, but also first order with respect to the catalyst, and the iodine doesn't appear in the rate expression at all. Now, a three-step rate mechanism has been proposed in order to explain this observed expression. The first step involves the reaction of the propanone with the catalyst. To form an intermediate. Now, this intermediate is unstable and decomposes in a second step. Therefore releasing the H+ ion again. The H+ is therefore a catalyst, since it is both used and released in the reaction and therefore is not consumed overall. The third step of the process involves the second intermediate reacting with the iodine to form the products. Now, in order for this to explain the observed mechanism, or the observed rate expression, the second step is the one that is determined to be the rate determining step. This works because the propanone appears once before the rate determining step, therefore doubling the concentration of propanone here will double the rate of the reaction, and the hydrogen ion catalyst appears once before the rate determining step, and therefore doubling the concentration of the catalyst will also double the rate of this reaction. Doubling the concentration of either of these will double the rate of production of this first intermediate, which will therefore double the rate of this second step. The intermediate produced by the second step is then immediately consumed in the final step, and therefore the concentration of iodine plays no role in the overall rate of this process, which is why the iodine does not appear in this rate expression. We can also represent this as an energy level diagram. We have our reagents, first reacting to form the first intermediate, notice the iodine hasn't been involved yet. The second step is the rate determining step and therefore has the highest activation energy in the process. Forming the second intermediate, reforming the catalyst, And finally, the final step produces the products. The only way to confirm whether this is actually the correct mechanism would be to isolate one or both of these intermediates in order to verify that this is indeed the pathway that this reaction is following. So although this mechanism does support the observed rate expression, the only way to confirm whether this is the true rate expression or not, it would be to isolate one of or both of these two intermediates in order to prove that the reaction is indeed following this path.